Okay, so this is actually take 2 of applying linear functions. The first time it cut off on me and I didn't realize it and I talked for way too long. Okay, so we're going to be working with word problems and analyzing and interpreting our linear graphs. So we have a word problem, and I've already started working on it here, but I will talk you through what I have done so far. So we've got a sporting goods store, and it sells cans of tennis balls. There are 3 tennis balls in each can. So the coach of the tennis team is buying supplies, and he needs us to write a linear function that relates the number of cans to the total number of tennis balls. And then we're going to graph that function. So first of all, we're going to define our variables. So T is our total number of tennis balls, okay? So that's how many we are going to end up with. N is the number of cans we have. Now, obviously, the number of cans will tell us the number of balls. So our T is actually our dependent variable. I'm just going to write that here. This is dependent on the number of cans, which is independent. Okay? And it's good to know that so that when we start putting all of this together, we can see how it all works. So the next thing that we want to discuss before we graph this is the difference between discrete information and continuous. I didn't write this before. Continuous data. Okay. Now, discrete data tells us that the space between the points that we are going to place on a graph have no meaning. So we actually would not be connecting our data, which I'm going to tell you I already did, so I'm going to have to disconnect my data. Okay, so anyway, continuous data means that as the line continues between the points, that each of those infinite number of points actually are part of the solution, and that's why you connect them. You'll see this as we go along and we actually apply it to this information. So first, let's go ahead and using our T, which is our T is going to be our number of tennis balls, and our N, the number of cans, we're going to put together our equation or our function, and we're going to say that T, the total number of tennis balls, is equal to 3 times the number of cans, okay? So each can has 3 balls. So if I have 1 can times the 3 balls in the can, I'll have a total of 3 balls. If I have 2 cans with 3 balls in each can, I will have 6 balls. So you can see how our function is going to work. Now we'll go ahead and we will put together a graph so that we can graph our function. Remember that we are talking about real data. So we don't have negative numbers of cans or negative numbers of balls. We only have positive numbers of balls. So here, and I'm going to just bring this out a little bit. Ooh, that's in. Bring it out a little bit so that we can see there at the very bottom. Bring it out just a little bit more. Okay, so you can see I've got my book here. I'll move that out of the way. Okay, so down here we are going to put our our independent variable, which is our N, which is the number of cans. And we'll spread out our data a little bit. So 1, 2, 3, 4, 5, 6, 7 cans. And on this side, it's going to be the total number of balls. Total number of balls. And this we will kind of keep straight here as we grow up. Got a lot of balls in those cans, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 21. Okay, so hopefully you can see that pretty well on the video. So I'm going to go ahead and put in my table of values. So I'm going to make a table of values, we'll do it up here, and we'll have N, our number of cans, and then we'll have 3N, and then we'll have our T, and 1, 2, 3, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. You can see how we're increasing. I really shouldn't have to do much more. I can just do it on the fly. So we've got 1 and 3 here. We've got 2, and we've got 6. We've got 3, we've got 9. If we had 4, it would be up here at 12. If we had 5, it would be up here at 15. If we had 6, it would be up here at 18. If we had 7, it would be all the way up here at 21. Now, the way we look at this data, it almost feels like, oh, let's draw that line here. I'm coming in a little bit so that you can see it. Let's draw that line, okay? But here's what I'm going to say. Are we going to have 1.5 cans? Well, no, the fact is he can't order 1.5 cans. He can order 1 can, or he can order 2 cans, but he can't order 1.5 cans. And even if he did order 1.5 cans, how many balls would that be in the half a can? Would we have 1.5 balls? I don't think so. So the fact is that we can't connect these dots because the space between the dots does not make sense. There's that question again. I always make you talk about that when we do word problems. Does your answer make sense? Just like here. Does a solid line make sense? No, because I can't go to any point on that line and have the data make sense. Okay? So if you have questions on that, we'll talk about that on Monday. Ooh, this is really tricky because I've run out of graph paper. So we're going to go to lined paper. Please don't do this at home because I have it available. Hopefully I won't make anything turn off while I make that switch. Okay, our next problem is going to be that we are drawing a graph, and of course, you know, forgive me. Like I said, please don't do this at home, but I didn't realize I was going to be out of graph paper at that very moment, and this is the second time I have done this. So I'm going to have to approximate. Okay, this is going to be where I put 1. So let's see, can I reasonably set this up and say, okay, 0.5. No, I really can't be reasonable here, can I? So I'm going to say we're going to be kind of, this is 2, this is 6. Right here, I'm going to go to, oh my gosh, I'll try to go in here to 4, and then I'll cut that in half. That'll be about here and about here. Okay, so this is, of course, 0. This is 0.25. This is 0.5 and 0.75, and of course here is 1. And then we are going to break this line up. This is a lot easier because I do have lines, and so we're going to do 2, 4, 6, 8, 10, 12, and 14. And I am going to be going, wow, this is going to be a little tough. So we're going to be at 2 at about here, and 4 is going to be just after this, so about here. So I'm just going to go ahead and put my line in as best I can. And once again, don't ever do this at home. Okay, so this gives us an approximation of what we are looking at on this problem. So the question is, suppose you draw the following graph. This is time in hours down here, and distance here, and our distance is in miles. Okay, and suppose you drew the following graph to represent how far you ride your bike at a steady rate. What is your rate? Okay, so you know, what we're looking at here is trying to figure out where things are crossing, and actually I didn't do badly here, because here's one of a really good place to look is at 6 and 0.5. So I'm going 6 miles, okay, every 0.5 hours. Well, 0.5, that's half an hour. So 6 miles for every half an hour. So if I double this, if I multiply this times 2, I'm going to have 12 miles in 1 hour. So this is 12 miles per hour. 12 miles per hour is how we would, you know, very often see it, but it's 12 miles for 1 hour. Okay? So it's taking data off of a graph that we have. Now, remember, this is a bike ride at a steady rate. Notice I draw a solid line, because at any point along this graph, you have an associated time and distance. Okay? So this is continuous data. Now, we've got a part 2 to this question. It is, if the graph had a slope of 10, what could you conclude about your bike ride? Well, obviously, my slope, my rise of 6 over my run of 0.5 means that my slope is 12, okay? So if my slope was 10, what could we conclude about that? Okay, so judging from the way this graph worked, I would say that if my slope was 10, that means my my constant rate, or my rate of change, is 10. Okay, which means then that I am going to be going at 12 miles every hour, every 1 hour, or 10 miles per hour. Okay, so that is how we read these graphs, and we're going to be doing more word problems on Monday. Hope you liked it.